Osmosis is a special type of diffusion. Up until now, we've been talking about the diffusion of solutes, things that have dissolved into water, or in the case of lipids, things that dissolve better into lipids. Osmosis is the diffusion of water molecules themselves. To understand osmosis, we need to remember that water is a molecule, right? Remember that we have water molecules. They look like this, with an oxygen and a hydrogen bound to it. They are polar because that oxygen carries a partial negative charge and those hydrogens carry partial positive charges, and that's one of the things that gives water its unique properties and characteristics. If we have water concentrated in one area compared to another, then water is going to move down its concentration gradient from high concentration of water to low concentration of water. And so it's fairly straightforward. If we were to look at that, if we were to concentrate water on this side, let's draw a couple of water molecules and look at it here. And so we've got water concentrated on this side. And let's go ahead and separate it by a semi-permeable membrane. Okay. And we're going to have this here, and my semi-permeable membrane will be here. And so here's my membrane, okay, right there. And like all semi-permeable membranes, it's going to allow water to pass through. And then we're going to actually say that on this side, maybe I have just a little bit of water. Well, then it's not hard to predict what's going to happen. The water molecules will move through that semi-permeable membrane to the other side until equilibrium has been established. Once we reach equilibrium, the water molecules will move back and forth equally, and we've reached what we call osmotic equilibrium. The problem with this is that we usually don't see a situation like this, right? Usually what we see instead is water, being the universal solvent, will have molecules on one side, little solutes on one side, and we'll just go ahead and throw in a few of these here. And so here's my solutes. And those solutes will take up space. And it's a little counterintuitive, but we could say that the solutes dilute the water. We can also say that the water dilutes the solutes. The solutes are dissolved in the water, okay? And so what we normally have is in a situation where we have a difference in water concentration, usually the other side, all that space will actually be taken up by solutes, okay? And so you can see here, total volume could be the same, but the amount of solutes per volume would be different. And in this case, you can see that we still have less water on the one side than we have on the other side. So we still have a difference in concentration of water, but it's the solutes that are creating that concentration difference, okay? And so you can look at this and you can intellectually understand that water is moving down its concentration gradient. And so we can say this in a number of different ways. The diffusion of water, so we can say water diffuses from high concentration of water to low concentration of water until osmotic equilibrium is established. This would be completely and totally and 100% accurate way of saying it. But we could likewise say that water diffuses toward the region of higher solute concentration. You've probably heard the phrase water follows the salt. Now, solutes are not always salt, so it's not a perfectly accurate phrase, but it still brings to mind the correct idea, the correct concept. Water will follow the salt. Water will follow the sugar. Water will follow the solute. It will move from a region of low solute concentration to a region of high solute concentration. Or alternatively, it will move from a region of high water concentration to a region of low water concentration. And this is termed osmosis. Now, osmosis is incredibly important when it comes to physiological systems, okay? And osmosis and its twin concept of osmotic pressure is super, super important when it comes to things such as driving water out of capillaries. Remember, we've got to get water. Oh, sorry, I'm gigantic already. Let me kind of use a less gigantic pen. So going back here, we're going to have my capillaries, and we've got to move that water out of the capillaries and into the tissues. Why? Well, water's going to carry with it solutes that we need, such as glucose. Okay? And so then conversely, we also need to be able to bring water from the tissues into the capillaries so that water can carry with it solutes that we don't need, such as carbon dioxide, and yes, some carbon dioxide does in fact dissolve in water. Not a lot, only about 7%. But anyway, urea definitely dissolves in water, and so that's a waste product as well. Acid is a waste product, and so we need to be able to move this water back and forth between different fluid compartments, and that occurs primarily by osmosis. There's another type of pressure. Let me back up and define osmotic pressure. Osmotic pressure is the pressure created by the solutes that move the water. Okay, it's the force that is generated by those concentration gradients. Okay, and it is going to contribute to the movement of water. Now, in some of the videos, the supplemental videos that you are asked to follow or watch, they're optional, of course, but they're available for you to watch. You actually will hear the term water potential. And I want to briefly define what that is. So water potential, the word potential suggests to the mind potential energy, which is exactly correct here. Water potential is the potential energy created by a concentration gradient of water. But that's not the only thing. So the concentration gradient of water contributes here to the potential energy that is stored in the water molecule. We have potential energy created by this concentration of gradient of high water molecules, high concentration of water, to low concentration of water. Remember that potential energy is the energy stored by virtue of position. And so we can see this and this storage of potential energy, and then when the water is allowed to move to equilibrium, that potential energy is released as kinetic energy, and ultimately we end up with potential energy of 0 once we've reached equilibrium. Nevertheless, there are situations where water is not allowed to travel, and in that case that potential energy remains stored. Okay, it remains stored, and that contributes to what we call the water potential. Now, that's not the only thing that contributes, though. There's another thing, and we're going to group this. Now, the videos didn't make this distinction, but I'm going to do this because I think it'll help you understand as we move throughout the pressure. There is another type of pressure that is very closely related to osmotic pressure, but slightly different, and that is called hydrostatic pressure. And in a nutshell, hydrostatic pressure, let's imagine a little balloon here, okay? So we're going to take a balloon, it's going to be a water balloon, we're going to fill it up with water. Well, the water is now trapped in that compartment. And certainly we have a concentration gradient, right? Lots of water in here. I only am going to draw just a few of them, but tons of water in here. Not so much water in the air. Maybe a little bit of water vapor. Okay, so we have this huge driving force that would favor the movement, theoretically, if it were allowed to move, across the balloon, the latex of the balloon. The driving force favors the movement of water into the atmosphere. Now we know that the balloon prevents that from happening until the balloon bursts. So we're going to assume that the balloon is intact. So we have this huge osmotic pressure. Okay, this osmotic pressure that is present due to the concentration gradient of that water. But why doesn't that water move? And the answer is that this latex pushes back against the water. And the water pushes against the latex. Okay, this is a law of physics. Okay, we have this law of opposition of equal and opposite forces. And so in this case, the water pushes against the latex, which is why the latex expands in the first place, and the latex pushes it back against the water. And the pressure that exists due to these opposing forces is what's called hydrostatic pressure, or you can say fluid force. And now imagine instead of a water balloon, we have an artery, right? And water does not move out of arteries. They don't. They move out of capillaries. It moves just fine out of capillaries. But the arterial walls are designed specifically to avoid leaking water anywhere. And so in those arterial walls, we have a situation with a water balloon where we have the water trapped within a container, and the water pushes against the wall of the blood vessel, or in this case the arteries, but we could say the veins, venules, arterioles, all of them would be kind of the same idea. It's going to push against the walls of this artery, and it's going to create pressure, and the walls of the artery are going to push back against the water and create pressure, and that would be hydrostatic. And that also goes into this water potential idea that was described in the video. And so for me, I don't usually use water potential as a vocabulary term in physiology. I'm more likely to refer to it as osmotic pressure and then hydrostatic pressure that we'll talk about. So just be aware of that. We're going to look at that. But I wanted to clarify that because it does show up in the videos and it can cause a little bit of confusion. All right. So if we look at water and the movement of water in osmosis and kind of apply this into the so what kind of category, what we're looking at here is an experiment that is often, it's a thought experiment that is often used in physiology to help you understand osmosis. So imagine, if you will, we have this U-shaped tube. And in this U-shaped tube, we have this selectively permeable membrane here. And this selectively permeable membrane, and by the way, anytime I set up a hypothetical or a thought experiment, I need to tell you the rules of this thought experiment. Okay, so in this particular example, the rules of this thought experiment, the membrane, I have to define that. And so we're going to say that the membrane is going to be selectively permeable, and here's what it's permeable to. It's permeable to water, but it is not permeable to any of the solutes. Okay? That's my rule right now. Now I can change that rule, so make sure when you are on the exam and you're looking at these thought experiments, I set them up, I say, you know, here's the situation. I would tell you the rules. Okay? I would tell you the rules. And so you need to look for those rules so that you understand and can answer the question correctly. In this example, this semi-permeable membrane or selectively permeable membrane, those terms mean the same thing, will allow water to pass through that barrier, but the solute cannot. So in this thought experiment, I'm going to fill up both sides of the tubes. And in one side, I'm going to put in an equal volume of, let's say I'm going to add 1 liter, just to help you kind of conceptualize this. 1 liter of a solution. And in the other side, I'm going to add exactly the same volume, 1 liter of a solution. Now, if you look at this, you can see these purple and blue dots. And what those purple and blue dots represent, the blue dots represent the water molecules, the purple dots represent the solutes. And so just looking at this, you can see that side B has more solute per liter. Okay? More solute per liter. And we could express that as moles if we wanted. We could express that as you know, a percentage, whatever we choose to do, we could express that. But regardless, we've got this solution where we can see more solutes per liter inside B. And that means that side B has the higher solute concentration. But conversely, it also means it has the lower water concentration. Okay, so those two concepts are related. The higher the solute concentration per liter, the lower the water concentration per liter. We're not used to thinking about water that way. Okay, so water's the solvent. Okay, so we normally don't think about it in terms of concentration, but it is true that the more solute we have per liter, the less water we have per liter. There's just room taken up by the solute. It prevents there from being more water. And so in this example, we can see automatically that side A has more water molecules and side B has less water molecules. Based on the law of diffusion, okay, water's going to move from its high concentration to low concentration. Well, the concentration, the side with this, the high concentration of water, is side A. And so the water will flow into side B through that semi-selectively permeable membrane. And as water flows into side B, the volume of side A will decrease and the volume of side B will increase. And this will continue until we reach equilibrium. Okay? It continues until we reach equilibrium. Once osmotic equilibrium is established, and what that means is that there's an equal concentration of solute per liter on both sides. Once osmotic equilibrium is established, then the net movement of water stops. Important to understand that it's net movement. We will still have some water molecules that are going to move towards side A, but that will be balanced by an equal and opposite movement of water molecules towards side B. And so the net movement of water is zero. The potential energy stored in that water concentration gradient is zero. And so we reach osmotic equilibrium. Now, osmotic pressure. The pressure is created by the solutes, okay? The pressure is created by the presence of those solutes and how they affect the concentration gradient. That concentration gradient is the driving force. We measure osmotic pressure indirectly. It's really hard to go in there and kind of tease out what the driving force is for these water molecules are based on concentration. But in this thought experiment, what we can do is if we take a little plunger here and we apply force downward, okay, the moment at which, okay, the pressure that we have to apply, okay, that is equal to the pressure created by the water in the solutes, that would be called our osmotic pressure. So it's an indirect way of measuring it. And so we apply force to prevent the water from migrating. The water has a driving force that wants it to migrate to side B, but now we're going to apply an equal and opposite force to side B to prevent that from moving. And that would be referred to as the osmotic pressure. Anyway, that's spelled wrong. Oh well, osmotic pressure. Okay, and this osmotic pressure usually is expressed in millimeters of mercury. And we're going to see this in practice when we talk about the pressures. If we go back, for example, to our capillaries, we're going to talk about osmotic pressure and osmotic pressure in the capillaries, and we might assign it a number, 7 millimeters of mercury, or what have you. And so that essentially means it's the pressure or the force that would encourage the movement of water into the capillaries under those circumstances. So that's essentially the term osmotic pressure and what it means. I like to think of osmotic pressure as a pull as opposed to a push. The solutes, this just works better in my head if I think about it as this pull. The solutes are pulling the water toward them. Okay, so the area that has the high solutes pull the water towards them, and the force that is generated by those solutes would be the osmotic pressure. It's easier in my head to think about it that way, and so maybe it's easier in your head.